All right, so today we are diving into a classic chemistry problem that, at first glance, seems totally impossible to solve. It's this fascinating scientific puzzle, a perfect little catch-22 that gets cracked with an incredibly clever trick. This quote right here, it gets right to the heart of it. To figure out the final amount of the stuff you're making, you need this special number, Kc. But to figure out Kc, you need to know the final amount of the stuff you made. So, where do you even start?
So yeah, let's break down this puzzle. We need to solve for this key value in a chemical reaction. The problem is, the formula itself basically demands that you already know the answer before you even begin the calculation.
At the center of all this is the equilibrium constant, or Kc. You can think of it as a scorecard for a reaction once everything has settled down. It just tells you the ratio of products to reactants. You know, a high Kc means you made a lot of product, a low Kc means not much happened. It's a really crucial number in chemistry.
Now, the specific reaction we're looking at is the key to everything. We mix two totally colorless solutions together, and they react to form this new thing that has a brilliant, very distinct red color. And that color, well, that's our only real clue.
And here's that paradox in plain sight. To find Kc, you need the final concentrations of everything. But to find those final concentrations, you need Kc. It is a perfect circle. So how in the world do you break out of it?
Okay, this is where the genius of the experimental design really shines. To break this loop, scientists figured out a way to, well, essentially force the reaction's hand.
The secret weapon is this ratio, 900 to 1. In one special standard solution, scientists add 900 times more of one ingredient than the other. It's basically a strategy of overwhelming chemical force.
So what does this actually do? Well, by flooding the system with iron, we make sure that the other reactant, the thiocyanate, has pretty much no choice but to react. It's called the limiting reactant, because it's going to get used up first. The reaction gets pushed so far that we can assume nearly all of that scarce ingredient turns into our red-colored product.
And this leads to an incredibly powerful assumption. For this one special solution, and only this one, we can just say the amount of red stuff we have at the end is the same as the amount of the scarce stuff we started with. This is what breaks the circle. It gives us a known concentration that we can actually work with.
Now that our paradox is broken, we can start gathering evidence, kind of like a detective. And our main tool? It involves measuring that red color.
This whole thing works because of something called Beer's law, which is actually pretty simple. The more of our red product there is, the deeper the red color, and the more light it absorbs. There's a machine called a spectrometer that can measure this light absorption very precisely. It spits out a number called absorbance, and that number is directly tied to the concentration. Okay, so now we set up our actual experiments. We create a series of different mixtures or trials. As you can see, the amount of iron stays the same, but we systematically decrease the amount of the other reactant. This is going to give us a range of different red colors, and therefore different absorbances that we can measure. So, we have our clues, these absorbance readings for each of our trials. Now it is time to crack the code and translate these weird numbers into the actual answer we've been hunting for.
Remember that special standard solution? The one with the crazy 900 to 1 ratio? Well, that thing is basically our Rosetta Stone. We know its concentration because of our key assumption, and we can measure its absorbance. This gives us a direct link, a conversion factor, between the mystery language of absorbance and the language of concentration.
So the process is really logical. First, we use our standard solution to figure out our conversion factor. Second, we use that factor to turn the absorbance reading from our other trials into the concentration of the red product. And finally, once we know that one value, we can use a simple calculation table, it's often called a Rice table, to easily figure out the concentrations of the other two chemicals.
And now, at long last, we have all the pieces of the puzzle. For each of our trials, we have the final concentrations for the product and for both of the reactants. We can finally plug them into the equilibrium constant expression and solve for Kc. The puzzle is solved.
But you know, in good science, solving the problem isn't the end of the story. You have to go back and check your work. And our entire solution depended on one big assumption. So, was that assumption actually correct?
Our entire solution, everything we just did, relied on the idea that 100% of that scarce reactant was completely used up. But we know that equilibrium reactions never truly go to 100% completion. There's always a little bit of reactant left over. So how accurate was our assumption, really?
Now, this is the beautiful self-correcting part of the scientific process. We can now take the average value of Kc that we just calculated and use it to solve the problem for our standard solution without making the assumption. We can find out what the real number is.
And here's what you find. When you run the numbers, you discover that, no, it wasn't 100%, but it was incredibly close. Maybe 99.7% of it reacted, with just this tiny, tiny fraction left over. So our assumption wasn't perfectly accurate, but it was more than accurate enough to get a very reliable answer.
And this brings us to a final, really fascinating question. This entire process was only possible because of an assumption that we knew from the start wasn't perfectly true, but it was close enough to be useful. It really highlights how science so often relies on models and simplifications to solve complex problems, which kind of forces us to ask, when is an assumption good enough?